Do you all see the presentation?
Yeah.
Okay. Well, then I'll start, no? So, well, hello everyone. I'm Julian, and I'll be presenting paper number 22, Cloud Leak, Large-Scale Deep Learning Models Stealing Through Adversarial Examples. Basically, this is a paper that describes a method to steal models in the cloud, no? So, brief introduction. Wait. Okay. So, well, deep neural networks have become the most common architecture on machine learning, no? But the problem is they depend on huge amounts of data and computing power, no? That's the reason why some cloud-based solutions have appeared that deal with this problem, no? And they have appeared with the name of machine learning as a service, no? MLAAS.
Julian, just so that I understand, the slide I'm seeing on your screen is called NSFW recognition. Is that what you intended to?
No. Wait. Is it moving right now?
Yeah, I'm seeing it moving. Okay, so you're.
Okay. Then okay.
Okay.
Sorry. Okay. Well, yeah, this is the introduction I was speaking about. So yeah, the thing with this MLAS is that they are in the cloud, and you need to pay for each individual query, and you don't have access to either the model or the training data. No? Some of these MLAS have certain extra features. No? Well, here I show some examples of these. Sorry, let me. Okay, some examples of these.
You can go to
you
can go to presentation mode. That might work better.
Presentation mode.
Yeah, the menu that you were doing, it had a presentation mode.
Presentation mode. Where? Here?
Yeah.
No, but do you see the change?
No. Okay.
That's.
I see. Yeah,
I don't know why
it
doesn't
I see.
shows how.
Okay.
Yeah, but well, I'll continue here. So yeah, you have this MLAS like Google Cloud Auto ML, IBM Watson Visual Recognition, Microsoft Visual Recognition, Face++ Emotion Recognition, and all these machine learning as a service platforms basically consist of an API that you can access through a web browser and just send send a query, no, with an input image, for example, and obtain a set of confidence values. A response, no, which is obviously has a cost, no. And well, here is like which MLAS services are attacked in this paper. It's basically all these 5 services: Microsoft Custom Vision, Face++, Emotion Recognition, IBM Watson Visual Recognition, Google Auto ML Vision, and Clarify Safe for Work API. Some of these accept customization, like transfer learning, submitting a set of training values to retrain the model, like those kinds of customization. They are black box in the sense that you cannot see what's in those models, like either the trained data or the model in itself. And they are monetized, no? You need to pay, no? So, now what's the motivation of the attack, no? Well, obviously it's to steal the model, no? To steal the model and create a substitute model in your local, for example, in your local system that you can use without paying any amount of money, no? Like you have, it's the objective is to transfer the model to a local representation, which you can use however you like, no? And the thing is that currently the attacks that have been used to extract these models only work for small scale machine learning models like linear regression, logical regression, support vector machines, but don't work for more complex ones as a deep neural network. And also current attacks require a number of queries to be proportional to the number of parameters, no? So with these deep neural networks, you have millions of parameters, and you in these previous attacks, you also need millions of queries, no? Which first is very expensive in terms of performance. I don't know, no? And second, it's like the APIs developer can detect, or maintainer can detect, obviously, if someone is making that such amount of queries, no? So then I'm going to introduce rapidly some concepts just in this paper, like transfer learning. You got this source model which you train in a certain data set that's similar to a target model, but in this target model you don't have that much that great data set, so you transfer part of the parameters to this target model. We also deal in this paper with adversarial attacks in deep learning. So we have already seen this, like you have these images, for example, that seems to be to classify to a certain label, but because of certain perturbations that aren't visible to humans, you can make them classify to another label. Model extraction attacks using queries, that what I have already mentioned, and active learning. No? Active learning being here the way a way of learning where the algorithm searches for informative samples and queries the user to label these samples, and basically it maximizes the performances of the training algorithm. And well, these concepts will be used in the paper, no? Well, in this attack, no? So what's the proposed method, no? And like a rapid overview. So to obtain input-output pairs from the victim model to retrain a substitute model in control of the attacker, no? Here we see the adversary. It queries the API with certain malicious examples. They are not just random examples. They're crafted in order to obtain a specific outputs that reveal the most of the victim model, no, of the API's model. And the substitute model works via transfer learning. Like you get, for example, a resident model pre-trained in a similar data set, and you just retrain part of that model with the input-output pairs obtained from the API queries. So basically the attack overview, no? And I'm guiding myself with this diagram also. So first, you generate the labeled adversarial examples as a synthetic data set, no? Here is here in this part we generate the adversarial examples that will be useful to query the API service to the API model. We obtain labels from those queries, and we generate a synthetic data set with all those input-output pairs. And those input-output pairs, we use it to train a substitute model. But the particularity of this substitute model is that it's based on transfer learning, where its first layers are like freeze, like you don't change those layers, are already pre-trained, but you do change the last layers with the input-output pairs. So these last layers of the neural networks are where the highest level abstractions are. And well, at the end, you based on retraining only these last layers, you obtain the model and you can generate a prediction. Now, I'm going to delve more into the details of this attack. So first, how do you generate these adversarial examples? Well, with a technique called margin-based adversarial active learning, no? So the goal here is to create useful examples for the synthetic dataset, which will be used on the substitute model for retraining, no? These useful examples should provide information of the affine hyperplane of the target classifier. In other words, like using this graph, that's this representation of a binary classifier, the affine hyperplane is the line that's between the circles and triangles, and what this how do you say, this algorithm, this learning method says is that we should try to obtain those samples that are close to the border of the classes, no, in that machine learning model, no, and those samples that are close to the border are usually the minimum confidence samples, no. So for example, in this case, the samples the most useful are the minimum confidence legitimate examples and the minimum confidence adversarial examples. In this case, they are represented by the pink triangles and the green circles in this image. And these are the most useful for the reasons I told you, because they're in the limit of the boundary of classes, no? So if you obtain that limit, it should be better than obtaining examples spread around the classes, no? Like maximum confidence adversarial examples or legitimate examples, no? Now, how do you generate those examples? How do you generate the synthetic dataset generation? Well, in this attack, there are 5 methods that are used. First is random samples. Like this is the worst performing form to get to generate the synthetic dataset. You only you have a set of images. You just obtain some random ones, and with those random images, you just query the victim model and obtain your input-output pairs. But like, it doesn't work that much. It isn't that good, no? Then we have the most better ways of choosing your adversarial examples. In here we have projected gradient descent, Carolina-Wagner attack, future adversary, and featureful. This paper proposes the last one, featureful, and we're going to discuss a little bit how these algorithms work. For example, I'm only going to gloss a little bit about this, but for example, projected gradient descent algorithm is just a multi-step iteration algorithm, no, that has a loss function and tries to optimize for the to get the best adversarial sample that isn't detected by, that does generate, that appears to be of a certain level, but the model thinks is of another level, no? We have the Carolina-Wagner attack, which is a little more it just like L2 distance, as a distance function, and it has here is the equation, and then we have the feature adversary. This and featureful use feature are feature map based, no? This phi case in the minimize, that should be minimized in this distance function are the feature maps of the kth layer, no? So this synthetic dataset algorithm to generate the adversarial example starts using some internal feature map features from the model, no? Like, one thing that I need to explain is that how do you obtain these feature maps, internal feature maps, if you don't have the victim model, no? Like for this to fool the victim model, where what has been revealed is that you can use a similar model to generate these adversarial examples, and then use it for the victim model. And the reason is that, like, if you have a model that's trained more or less in the same data set, this paper says that the class boundaries are more or less the same. Well, not that exactly, but you can get a similar boundaries. So you can use the same substitute model to generate the adversarial examples, and then you can retrain that substitute model. No, like you use the substitute model in two cases to generate the adversarial examples that are used in the victim model, and then you use those victim model input-output pairs to return that same substitute model. No? And here finally we have the feature fold that also uses the feature map internal values. It uses a distance function based on LP distance. It has a loss function. And the loss function is constrained by a variable m, no? And yeah, I'm not going to be on detail about how this works, but it's basically another form to generating these adversarial examples. So basically how this all works, featureful. Well, you have your source image, you perturbate the image, and you have the guide image, which classifies for the label you would like the source image to classify. You know, you have the feature extractor, where you obtain the features you want to compare to minimize the distance between for example, the source image with perturbation and the guide image. You have the feature extractor, with, in this case, is the our substitute model, and you obtain the salient features for each layer, for each feature map layer, and you try to minimize the difference between the source image perturbation input and the guide image input, so to make it indistinguishable. To make it an adversarial example, no? And for this you use an LFVGS optimization algorithm, basically. And we have an evaluation metric to evaluate the performance, the accuracy, between the victim model and the substitute model over a data set test data set. And finally, this is our training algorithm. If you see here, there's an FV, which is the victim model, the model we query with the API. The FS is the substitute model, which is in our system. X0 through XM are the input images, and we want the retrained substitute model. No? So it's an iterative algorithm. We have and the maximum number of iterations are m. So here we see that to craft the adversarial examples, we have the adversarial examples generator. Here the proposed one is featureful, and here we see that it uses the input images and uses the own substitute model to generate these adversarial examples. To generate these adversarial examples. Then we use those generated adversarial examples in the victim model to generate the synthetic data set, and then we use that synthetic data set with our substitute model to retrain it. No? And for this we also use the transferred model. No? So you iterate this through all the images. And here are some of the results. Here we see some of the services, models, number of queries made number of queries made in that particular model. And we see here the performance, the accuracy of all these adversarial example generating algorithm, random samples, graded descent, Carlin Wagner, feature adversary, feature full, and we see the price. No, like this, a quantity of queries corresponds to a certain cost. No, between the parentheses are the accuracy relative to the accuracy of the original of the victim model, and outside of the parentheses is the absolute accuracy. No? So we see that in almost all cases, featureful outperforms the other algorithm, no? Except in some cases where Carly Wagner outperforms those featureful, no? Yeah, basically that. No? Well, here's a more detailed view of each generative adversarial example generative algorithm based on the transfer learning architecture and based on a certain quantity of queries made. And here we see the accuracy depending on all those factors. Here, the green bar corresponds to the featureful, the technique proposed here, and we see that in traffic recognition, in that model, it outperforms every other model, but we see also that Carly Wagner isn't that much it's also presents a good performance. No? Here is the same, but with flower recognition. Here, for example, in the transfer learning architecture ResNet 50, in budget C, we see that Carly Wagner outperforms featureful, no? But in all other cases, it's mostly featureful that outperforms the other. Emotion recognition, same results basically. Not safe for work recognition, also, no? So comparison with other existing attacks, no? We see in these four parameters, being parameter size, queries, accuracy, cost, that the new method, called here our method, outperforms the other attacks, no? Because it allows to obtain the most parameters possible, like 200 million, with less queries possible, with only, in this case, 3,000. It has a high accuracy and a low cost, no? Compared with the others. Like all these parameters in as a group, but yeah, it outperforms the other attacks, no? And here we see some graphs like comparing all these attacks with the accuracy obtained based on the number of queries. We only see that in traffic recognition, PaperNote and this method are have this almost same accuracy, but in the others it clearly outperforms all other attacks. Now there was in the paper it mentions that there was a defense mechanism.
Julian, can you wrap up? I think you're well above the time. So
okay, yeah. So yeah,
maybe just jump to the conclusions.
There's a defense mechanism called Prada, but it doesn't work with this attack. Like what I'm saying is that it misses, it doesn't detect really the attack. Then in this paper, a new defense detection detection mechanism also proposed, which is has better success. Some limitations of all this work is that when generating the adversarial attacks, sometimes there's a lot of perturbation made, so there's need to be further work to try to make this perturbation the less. So the substitute model doesn't lose its accuracy. There's also talk about further work in extending this attack model to multi-label cases, because in this case it's only single label cases. And obviously, in this case, you only deal with models corresponding to images, but it should be great to extend it to other domains as audio or text, no? That's all for now. I don't know if there are questions here.
Yeah, anyone questions? Great. Thanks, Julian. I think in the interest of time, would like to move on. So I think Vivek, you are next. Right?
Yes, sir. Hi everyone. Can you hear me well?
Yeah.
Yes, very well.
Yeah. So I'm going to present membership inference attacks against machine learning models, work done by Reza Shokri et al. At Cornell Tech. So as Julian discussed, there's a plethora of machine learning as a service right now offered by Google, Amazon, Microsoft, every big giant, which allows you to simply input your training data and without any in deep knowledge about machine learning, train advanced models, and it gives you a prediction API, which actually gives you the classification in terms of predictions for each class for a given input data. So, what is privacy in machine learning? So, in the ideal case, as discussed in Talenius Desideratum, which is for any given database, a model must reveal no more additional information than the input itself. So, this ideal case is not achievable in machine learning. So, over here, we discuss about privacy of data being used for training. And we particularly discuss membership inference attack, which lets you know if the given a data point query was it used for training or not. So this can leak a lot of important information. Consider the case that there's a network being built to determine the dosage of medicine for a particular disease. If you get to know that a person's data was used for training it, it implies that that person has the disease. So it's leaking a critical information. So the attack model assumed in the paper is that either the attacker has the access to the platform where the model is being trained, or at least it knows what's the model in black box sense. So it doesn't know anything about the parameters or the additional information like how, like what kind of hyperparameter tuning and additional stuff is being done. But it does know what kind of model is being trained and what exactly is there in it. And it might have some knowledge about the population, but does not have direct access to the complete population set that is being used for training and testing. And it just has the data record and black box prediction access to the API. So what exactly the membership inference attack does is that there is a difference between this classification output from this prediction API for a training data and a testing data. So this difference needs to be recognized, and based on this difference, we can tell whether a data point is used for training or not. So the most clever way right now to do this would be to use machine learning against machine learning. So how do we attack? So as I discussed that we have limited number of queries and limited information on the parameters. So what we need to do is that first for each class, as this prediction distribution is different, we need to train the attack model for each class. And the attack model is nothing but a binary classifier, which lets you know if the data point that you have is within the training set or not. So essentially, is it a member or is it not? So in the paper, they have proposed a new method of doing this called shadow training, which utilizes the shadow models. So a shadow model is nothing but the copy of the victim model in a black box sense. So there is no real training data available, no test data available, but it says that these shadow models are almost like the real model. And given that most of it is done in the MLAS services, so if you have a similar kind of training data, but not exact similar, not the same, and when you use this similar kind of training data to train the shadow model, there is no reason that Google would give me a different model than you for the same data set and the same classification task. So this is what is being utilized, and using multiple of these shadow models which are similar to the victim model, we train them, and then based on their prediction APIs, the binary classification is trained. So each of this prediction API from shadow model is like a data point for this binary classifier to train on. So as we discussed that there is no training data available, so the fundamental assumption that the paper makes is that the worst case assumption where the training data is completely disjoint from the real training data. So there are three possible ways that the adversary can generate the data from. One is the model based, where what you do is start with a random data sample. As you know what features it will have, but you really don't know what the data record is. You just generate a random data point, and then using some search mechanism like hill point search or something, first you determine which class you're targeting and try to figure out the data in the data space. So it's like you keep altering the data point in a systematic way till you reach the point where you have the data record that satisfies your requirement. Other one is that you have some marginal distributions of features, some statistics of the data set. So using this statistics, you try to generate a data point. And the third one is that there is no real data, but he has access to some noisy data set from the same population. So how is the training done? So first you have a single random record which you use to the ML AS platform, and then check the prediction API. If it meets your requirement that you're getting the exact, so they say that if there is a high certainty in prediction, it means that it is coming from training than testing. So if there is a high prediction for that particular class, you can assume it to be training data point. So you generate training and test data similarly for each shadow model and train all of the shadow models. Now using this shadow model outputs, you train your attack classifier for each class, and then when a new record comes, you take the prediction API's result and put it in your attack model, and then check whether it is a member or not. So in order to evaluate this, as it would be difficult to do it on a larger complex data, as you can see, they have chosen very small data sets. So one of them is purchase data set, which has 600 binary features. So it is very easy to move across the space, as each feature just has a value of 0 or 1. So based on these, they have generated using all three models, and they run it on Google's service and also perform the same attack on local neural network models that they have trained. And for this particular data set, they have used 20 shadow models. So and then the attack classifier is made using the same service or a neural network with one hidden layer. So it could be made with anything, but for this paper, they have used this. And the accuracy is determined in terms of precision and recall. So this is the first evaluation where they show that even with having the noisy data access, you have a similar accuracy to the real. And over here, there's cumulative fraction of classes, which means that the cumulative fraction 1 means that it has been trained on all the classes, and you have an attack model for each class. So similarly, like if it's 100 classes, 0.1 would mean that 10 classes have been trained, and even 10 classes you get accuracy of 0.6. So this is based on our three models. So if you have the real data, this would be the curve, and if there is a model-based learning, this would be the curve, and this is the marginal synthetic base, which means that they have sampled from the distribution and tried to create the record. So why does this attack work? One reason is that overfitting, as we could clearly see that when a model overfit, it usually performs well on the training data, but bad on the testing data. So this is one of the reasons, but not the only reason. Even if there is no overfitting and very less of overfitting, there is always an uncertainty between the testing data and the training data. So as you can see the curves here, it shows how different it is for prediction accuracy of the training data and like the uncertainty in predicting the training and testing data. So what it essentially relies on is that the target model does not generalize well on the complete data set, and the training data is not very diverse, or it is somewhat concentrated in a limited space. So in order to mitigate this attack, one way would be to reduce overfitting, but as you can see from here, reducing only overfitting would not help much. Other strategies would be to reduce the prediction to only top K class. But again, as you see here, even reducing it to top 1 class can leak some information. And then, like, based on you can increase the entropy essentially by involving some term like temperature, which is actually normalizing sort of the softmax function. So it is in softmax function in the exponential term, you add another factor over there, and otherwise it is like you could add some noise, or you could just reduce the prediction limited to some fraction point. But the most efficient method would be to use differentially private models. But again, as discussed, differential privacy has its own trade-off. So if you use differential privacy by removing some features, you're trading off with the model accuracy. So the strength of this paper is that it is robust to imperfection in the training data. So like as we discussed earlier, even with the noisy data, it performed really well and almost close to the real data. And then it can be implemented even if there is only top 1 predictions available, and it is having to require minimal information. And for the data generation, there are easy search algorithms like hill climbing available, which one could utilize to search over the space. The only weaknesses are like it is not applicable for large data sets. It is only applicable for small and less complex data sets. There is no quantification and optimal strategy currently shown in the paper for the number of shadow models. It just says as you keep increasing the shadow models, your accuracy increases. But again, that would depend on how much of synthetic data you can generate. And it is only restricted to, again, single label class classification. And it is not shown to work in multi-label or regression cases. So that's it. Any questions?
Thanks. So yeah, anyone? Thanks. So anyone questions? Well, okay. So let's move on. In that case, thank you, Vivek. So I guess next up is Michael, right?
Hey, hello.
Yeah. Okay. Yeah.
I don't have a camera on, or it doesn't work, so I'm sorry about that.
Doesn't matter. It's just screen share.
Okay.
Although you might want to get a camera for next quarter. So.
Yeah. All right. For my paper, I'm presenting Helen, maliciously secure cooperative learning for linear models. It's a research work done by a group in UC Berkeley. So for the contents of my presentation, I'm going to go over the issues and their solutions and some background that makes the solution, why the solution works, the implementation details, the results, and some final thoughts about the work. So for the issue, you have multiple organizations with the same interests, but they have different data sets. And most of these data sets are privacy sensitive. For example, you have patients from different hospitals with different medical records, or banks just trying to detect money laundering, but they don't want to give out details to their competitors. So almost all organizations refuse to share their data sets with each other, but they want to create a comprehensive model. So Helen is the solution to this problem that they're trying to do. So they coined this term called cooperative or cooperative competitive learning. So what it does is that organizations, they train on their own data sets, and then after each iteration, they share their partially trained models with each other. But at the same time, they assume that all the other participants may be malicious in that they could be trying to poison the data, or they're just giving bad results to each other. So I'm going to go over some background terms that are used for the implementation. So one of the solutions used is something called a threshold partially homomorphic encryption. In that, it's that a public key encryption scheme in which some form of computation can be done on the ciphertext, but it requires enough participants to make the secret key. So essentially is that they come together, they generate a secret key, but each participant only has part of the secret key. But everybody has the same public key. So in Helen, they use Pyler. So how Pilot works is that you get two ciphertexts and then you multiply them together, and then when you decrypt it, you get the sum of the two original plain texts. Another method used is something called zero-knowledge proofs. So in zero-knowledge proofs, the prover needs to prove that they're the actual person that they're claiming to be, but without revealing their own secrets. And so Helen uses a protocol called plain text ciphertext multiplication and ciphertext proof of plain text knowledge. And later on, I'll explain that it's used in these modules called gadgets to prove that they generated or provided the correct data throughout the entire cooperative computation calculation. And then lastly, they use something called malicious multi-party computation. So usually you have an adversary that's attacking from outside the system. They're trying to gain entry into the system. However, in a malicious multi-party computation, the adversary is part of systems. So essentially is that they can't trust each other. And the goal of malicious MPC is to protect the privacy of one's own data from another. So they don't want, so going back from the previous examples, for example, hospitals, they don't want to share each other's data with, they don't want to share each other's patients' data with each other. And so Helen uses a protocol called SPDZ. It's essentially a protocol that allows them to share data sets and computational results securely and the goal of it is to prevent them from leaking any information from their data sets. And SPDZ has two phases of its own, an offline phase and an online phase. So for offline phase, it generates pre-computed values that will be used to exchange during the online phase. So in Helen's use case, it would be generating weights for their trained data sets, and then on the online phase, they will exchange these weights, and then also at the same time provide signatures for these weights to verify that it did come from the intended person or party. All right. So for implementation, Helen has 5 implementation phases. So the first one is something called an agreement phase. In the agreement phase, the parties come together to decide on what algorithm to use and then what type of linearization models they want to use. After that, there's something called an initialization phase. This is the part where it uses the threshold partial homomorphic encryption. So here they would generate the encryption keys in which everybody has the public key, but only a part of the private key. So as you can see in the figure, everybody has the global key and then part of the private key, and then they also share the encrypted data summaries to each other. So I'll go over that later. And then at the same time, each individual still has access to their own database, but they don't know about each other's other databases. So next phase is called input preparation phase. So here the participants compute summaries of its data and share the encrypted summaries with each other. And each party needs to prove that they know its own summaries using zero-knowledge proofs. So how that works is that they do SVD decomposition on the plain text data. And when you do SVD decomposition, you generate these submatrices. And so there are the properties in these submatrices that can prove that the participant knows, that the participants can prove to each other that they know that it's from their own. The paper itself goes into a lot of math, but from here, I'm just going to give a brief overview of how it works. So when you do SVD decomposition, you get one of this matrix. And when you encrypt and when you calculate the transpose with itself and encrypt it, you should get close to identity. And also from SVD, you get a diagonal matrix. And in that diagonal matrix, there contains a public value. So they need to prove that the diagonal matrix contains a certain value added with a public value. And here, this is where the gadget 1 and 2 come into play. So a zero-knowledge proof for the statement that if you have the public key and encryption of three partial encryptions and the private parameter X, then if encryption Z is composed of X, decryption of X and Y, then I know X such that the encryption X is equal to X. And then for a different one, gadget 2, given public parameters and a public key and 3 encrypted values and private parameters X and Y, and that encryption Z is composed of encryption X and encryption Y, then I know X, Y, Z, such that I know encryption X is equal to X, encryption Y is equal to Y, and encryption Z is equal to Z. Finally, after when they exchange or prove that they know each other, that they provided the correct data, then it begins the model compute phase. So each party will calculate using their own locally encrypted data. And afterwards, they will share the encrypted weights with each other and prove that it was done correctly also by using zero knowledge proof. So to prove that it was them who calculated their own weights, each party will generate a random value and also broadcast the encrypted value. Then each party will take the published value and compute the product with the ciphertext. So this is where the Pyler encryption comes into play. After that, each party will decrypt the results above to get the plain text. And this is how they built something called Gadget 3. So if there are n participants and each party has a public key, but only part of the secret key, and there is a public ciphertext that everybody knows, then each party will just take a part of their share and decrypt it, such that the summation of the summation of the entire encrypted text modded with a module P, or module with a value P. So P is the encrypted random value that everybody has once they broadcast it. And so it still protects the privacy of each other's participants' private data, but they only extract the part that they're supposed to get. And finally is the model release phase. So after iterations of training, then everybody will get the weights and the final model. So to make this work, each party it is possible that each party may try to mess with the data during the malicious multi-party computation transfer. So for example, after I've calculated my weights, I may try to tamper with it and then re-encrypt it and try to share it with everybody. And that is possible. So to prevent this, each party needs to verify 3 values, and that these 3 values fall within a given interval. And this is something called interval proof. And to do that, each party will compute 2 more values and then encrypt it. And they'll also generate a random value along with these encrypted values. Afterwards, each value is broadcast to everybody, and then they will use the encrypted random value to perform a joint decryption. And then after you perform the joint encryption, you need to check that the partially decoded ciphertext also falls within a range of values. And if it's not within a range of values, then it means that somebody has tried to tamper with it. And if it does, and if everybody's part of their share matches or falls within a certain range, then they need to release their part of their secret key to verify the computation has been done correctly. And this will implement Gadget 4. So given public parameters, encrypted values, ciphertext A, and an encrypted SPDZ input share. So in the SPDZ protocol, they also generate some values that are used to verify that it is from the right party. And in SPDZ max, or multiple authentication. And then interval proofs of plain text knowledge. You need to verify that the public knowledge, if you take the summation of part of it and mod it with a public value, and that these values are within the SPDZ ranges, and that these the ciphertexts are valid within the multiple authentications. They prove that to the party that during the transfer, the data was not modified, and that the computations of the weights were also done correctly from the previous phase. There's a lot more detail in the paper, but I've really skimmed over it. It goes into the full model and mathematical proofs of how it works. And then for the optimizer, they decided to use something called a alternating direction method of multipliers. So in ADMM, it's scalable because each party just needs to work on their own data sets And so basically they're optimizing for their own local data sets. And afterwards they can share with other parties. Whereas in SGD, you have to iterate over the entire data sets, and which is a problem because the parties are not supposed to share with each other's share their data sets with each other. And so here are the results of Helen versus a baseline model of SGD using SPDZ protocol. So they had two data sets. One is a gas sensor, and then where it's just a chemist doing mixtures of two gases and their results of these mixtures of these two gases. Another one is a song data set. It's supposed to be a collection of songs from the 1990s. And for Helen, most of the overhead is spent on the model computation instead of doing the secure zero knowledge proofs using SVDs. However, if there are more features to be used, there is considerable overhead in doing SVD decomposition and its security proofs. So as you can see in the bottom right, as you scale the number of features, the SVD proofs start to have considerable overhead. And if you have more parties want to do cooperative training, SVD proofs is not much of a factor. Instead, it's just the model computation that is scaling linearly. And then on the left is a breakdown or a runtime breakdown of the steps or the phases. So here they grouped 3 of the phases into one. It's called MPC offline. But yeah, in the baseline, there's something called secure SG. It's just SGD with SPDZ, like I said before. So there are M parties, number of samples, and D features. And the overhead is considered as M squared because for every party you add, you also need to know their data. So it's essentially M squared. And then for SVD decomposition, it's just D squared because you have a matrix decomposition. And then same with the SVD proofs, D squared and D cubed for verifying your own matrix and also verifying each other's matrices that you get. So for Helen, the baseline improvement over the gas results is roughly 20,000x improvements. You can see on the top right. Here, the red and green is the baseline, and then this is what they predicted. So as the number of samples increase, it can take about 3 months, whereas for Helen, it takes less than 30 minutes. And then on the bottom right is the song database. Again, if you use SGD with the SPDZ protocol, it can also take roughly a week to 3 months to finish training, whereas Helen takes about 1.5 hours. From the graphs, they have Helen. There's something called Helen input preparation. Again, they just group the parts of the zero proof knowledge, the SVD computation, SVD proofs together. And it scales very slowly because SVD computation is primarily fixed. Number of inputs is primarily fixed. And then for the model compute phase is also pretty flat because when you use the ADMM optimizer, the number of iterations required is very small. Something like only 10 iterations is needed in their paper. So yeah, in conclusion, Helen works even when when everybody assumes it's malicious. So previous state-of-the-art works requires that you outsource your data to non-colluding servers and that it only works between 2 parties. However, Helen does not protect against membership inference-based attacks as presented in the previous papers. And Helen cannot prevent users from feeding bad data in the beginning. However, it will require that the malicious actor will have to use the bad data throughout the entire computation phase and sharing phase. So yes, thank you.
Great, thanks. Anyone with questions?
I just have a quick question, if possible.
Sure.
Yeah.
Okay, so from your first or second slide, I'm a bit confused. Does it do any processing on the data as if like they're looking into the data, or is just to make sure that it's like becoming encrypted when they're sharing the data among like different hospitals or something? And also, do they like get rid of the names of the hospitals? Because imagine like if one hospital knows like is from another hospital, then probably there is some chance to kind of decrypt that data or something like that.
Okay, so in the hospital use case, or as you stated, so what they do is actually they only train with their own data sets, and then after they train with their own data sets, they share the weights or encrypted weights. But there's something called a summary, and so the summary is effectively a signature or a proof. It's sort of like the public key, private key infrastructure, but you have a signature that goes along with it to prove signature to prove that it was coming from you. So they don't actually share the data with each other. Instead, they just share this signature, but they cannot see what's inside the signature because of zero proof knowledge, or the zero knowledge proof that they need to do.
Got it. Thank you so much.
Yeah. But they only share the weights with each other.
Mm-hmm.
Yeah.
Okay, any other questions?
Yeah, I was wondering like the practicality of Helen when implementing in edge devices. So basically they're saying that SPDC cannot be run on edge devices, but that's sort of not true. And I've seen that for the test, they're like using server class machines. So like how scalable is it if we want to like do like n-party computation on edge devices?
Yeah, I think there's stuff. I mean, this is targeted at the more traditional use case where the discussion just now that there are a bunch of hospitals and they want to collaboratively learn some model over the entire population, but they don't have the authority to kind of release the subpopulation level data and all. This is not really the edge device type situation yet. On the other hand, I mean, the factor improvements they're showing are pretty tremendous. So yeah, I think your group should check it out because your project is in kind of the
yeah
space.
We did. I mean, like they're basically like they're based. I mean, they're using the SPDC, which we are also using. So basically, I mean, I don't think they're going to get like significant performance improvement if we consider like, simple cases, for example, like reducing time for queries or trying to reduce network latency or something like that. Because basically all they're doing is that like they're just modifying the linear regression training algorithm and just adding like their own zero knowledge proof.
It does have, I mean, the zero knowledge proof idea seems pretty cool. So actually, just as a side note, so firstly, I mean, if you think about zero knowledge proof, what it is saying is that like I'm claiming that I know something without actually revealing that secret, right? So it's a pretty cool concept. Actually, the person it was invented or discovered, I don't know what's the right term, by Professor Rafi Ostrowski in CS department back when he was doing his PhD. So there's kind of a UCLA connection to it. I also wanted to kind of, between these three papers, the first three papers, we have seen kind of three different ways ML algorithms, machine learning systems are getting attacked, right? So the first presentation, Ulian's presentation, is kind of really theft of intellectual property, right? I mean, I'm running a service, I put in a lot of time and money to create it, particularly collecting labeled data and all is pretty intense, and then here comes someone who, with a small number of queries, essentially is using me as kind of labeled data generator of sort, right? I mean, it's basically bypassing the costly steps, replicating the service. So intellectual theft is the issue out there, and that is also present, as you might imagine, in kind of these algorithms when they get built into edge devices and all, right? I mean, the scenario in that paper was the ability to query a service, but you can imagine these things also in edge context where the firmware has this kind of information. The second paper kind of really looked at the membership inference attack. So the model itself is leaking leaking stuff about the training, so there is a privacy violation which is happening. The third one, which we just saw, is really looking at keeping data private during the process of training, right? There are some other attacks also on ML systems, and so one is, which is, I think it's so one of the project groups is exploring that, which is adversarial input, which is, and we kind of saw references to it in some presentations today, but which is basically at inference time, can I subtly manipulate the input so that a human looking at it won't realize that it has been manipulated in some way, and yet it will cause the machine learning system to yield a wrong result. So whatever the image of a car, manipulate it subtly so that it will not be classified as a car. It has obviously implications in terms of safety and such that one might encounter, and there are kind of special cases of it, whether you are manipulating the digital file or whether you're mounting these attacks while you're still in the sensing domain. So attacking the input is one. Another one which has emerged is compromising the training pipeline. So we saw in this work, we are trying to maintain privacy, but what about when someone compromises the training data or compromises the training algorithm, like for example in this case making sure that each party is doing its is not trying to manipulate so as to subvert the model. So these are called backdoor attacks, essentially inserting a backdoor so that the final product model has some weakness which can then be exploited at runtime. So typically the scenario is that maybe I'll make sure that the trained model, whenever it sees tanks of a particular country, will not report the tank, something like that. Okay, so basically we inject a weakness into the model. So those are two others, and there are other kind of scenarios that people kind of keep talking about and all, but at least these are kind of the 5 major attack scenarios around which research currently exists, as well as of course defense against them. How do you create models which are robust to, let's say, adversarial input, or how do you detect backdoors in a model? So I give you code for a model, can you figure out whether it has been compromised, and that maybe whenever it sees a yellow post-it yellow post-it note, it will behave adversarially. So and so on and so forth. So for each, so we have attack work and kind of the defense work going on. So pretty cool stuff. And I guess also there are things happening on kind of the platform side which has implications, like for example, can two models being trained on a GPU steal each other's data, things like that. So there are other types of more systemish attacks that we will also explore. Anyway, so we'll move on to the 4th and 5th paper then. So these are kind of different in their flavor. So I guess Jennifer, you are up next. Are you speaking? Because I can't hear you. Hello, Jennifer. Can anyone else hear Jennifer?
Oh, I can't hear anything.
Yeah, Jennifer, we can't hear you.
Is there audio mute?
Yeah, I think her microphone doesn't work.
She can call in through phone if she has a phone.
Check your audio. Have you left it on mute by any chance?
Call in, Jennifer, through the... Oh, you don't have a battery? Uh-huh.
Can you guys hear me now?
Yes, we can hear you now. Thanks.
Okay.
Yeah.
There we go. And can you see my screen?
Yes.
Okay, perfect. Let me go to presentation mode. Sorry about that. Okay, so this paper is about brake data-based location tracking in usage-based automotive insurance programs. And the paper reference is there below. So this one basically, this paper talks about usage-based auto insurance using brake-based location tracking, and that's where you get a discount or a penalty in your auto insurance based on your driving behaviors. So they adjust prices based on vehicle usage, how fast you're going, what your average mileage is, that kind of thing. And in this paper, they based it on CAN bus data, so that's over the OBD2 port. And in this paper, they only analyze braking habits, although you can get this kind of, you can get additional data from that port. So the objective of the paper was to determine what can you learn just by analyzing braking habits specifically. So if you're an adversary, what could you learn about the person from this information alone? So first thing they did was they categorized applied braking signals using an LSTM full convolutional deep learning model. They identified the number of intersections based on these maneuvers, and then they used the graph-based search algorithm to find the vehicle routes. They estimated what was the most probable path based on commute time, distance, traffic signs, things like that, and they cross-referenced that data with known map information. So if you look on this little cartoon, basically they categorized 4 different maneuvers. So full stop was you're stuck in traffic, you're totally dead. Second one was slowing down, so like if you're on a curve or you're merging, and then left turn, right turn. So, and they proposed, okay, what attack could they do with this information? So they're trying to figure out the location and time that a person was on the road and where they were going. So what they did was they obtained the brake signals using the CAN bus. So they looked at brake pressure magnitude, brake signal duration, and then total driving duration. And then the data set, they had 24 people, mostly young folks, and most of them, or well, about half, drove to work regularly, so they got a lot of data on that. And then all of them had the driver's license between 2 and 12 years. They all drove the same car for this particular test, and the data was collected at 100 hertz, and they collected it over 5 months, so they got a good range of traffic patterns, things like that. So their attack was they got this raw data of brake signals, they identified the driving maneuvers, then they identified the nodes and edges of the paths. They had a speed profile prediction based on brake duration and magnitude. And then they searched this against known paths in that region to see what matched. So if we're looking at brake maneuvers, this is what each of these look like. So if you look at brake length, if you're doing a left or a right turn, they really don't look all that different. So brake duration, you can't really distinguish these two as well as you can the others. So full stop looks like this. So you kind of see a much different pattern than you do for left or right turn. And then same thing with slowing down. So they were able to say, to gather this data and say, okay, this is what a left turn looks like, this is what a right turn looks like, and then this is what these other maneuvers look like. They also looked at average brake signals, which is brake magnitude divided by the length for the forward driving maneuvers. So normalized braking for each of the maneuvers is here. So that's kind of their pattern for identifying maneuvers. Okay. And then they also looked at speed reduction and acceleration, and they determined that speed reduction varies linearly with the applied brake duration. Kind of makes sense. And they also looked at acceleration patterns for the driving maneuvers, but they were not statistically distinguishable. So they kind of all overlapped in this shape. So how did they get from that data to estimating someone's path. So they ran a long short-term memory fully convolutional network with a classifier algorithm. They used 17 of the participants to train, and 6 they used to test. So as an example, this is how they determined the time interval. So they had time period required for, based on the raw data, time period required for maintaining the traffic flow, and required for reaching the traffic current speed. And they did make the assumption that most people obeyed the traffic laws within 10 or 15 miles an hour. So that was kind of that was their assumption. So they didn't have any outliers with crazy speed type drivers. And then they ran this function to learn the acceleration patterns based on the data. So this is the curvature of acceleration, and then this is the asymptotic upper bound, which is proportional to the current flow of traffic based on their mapped data. So then they went on, they said, okay, now I have these classified, I'm going to make my path prediction. So they used OpenStreetMap API, and they converted it into a road network graph with almost 10,000 nodes and 20,000 edges. And they did a path searching algorithm and clustering techniques, which basically determined, okay, when is somebody turning, determine they determined the distance between when somebody made a turning maneuver, and then we're able to determine what a straight path was. So this is traveling time at the edge, this is the length of the edge, and they were able to also estimate traffic signs within this. So one of the hardest things for this model to understand is if you had a long period of time where you were just coasting or you didn't have to apply the brake, those are the biggest unknowns. So taking all this information, and yes, again, assuming all drivers obey traffic rules, they don't run any stop signs, that kind of thing, they computed the most probable path, and they scored all of the candidate edges. So they tested this against both dense paths with a lot of turns, a lot of stops, you're stuck in traffic, that kind of thing, and then very sparse paths where there's not a lot of turns, not a lot of stops, and there's long times between braking. So they tested at both extreme cases. Experimental results, so they ran this again over 5 months, and the predicted routes were scored against the actual route. So they did know in this experiment where the drivers actually went, and were able to compare their model with the actual route. So there, as you can see, there's very high precision and high recall for driving maneuver identification. The authors ran this against a random forest method as their test baseline to see if their model was any better than current existing models of that type. So if we look here, if you can see it, the actual path is in red, and they had the kind of medium, least error, most error paths, and they used their model to predict which was the most likely path of all the possible paths in their that their model predicted. So you can see that for part of the routes here. Any questions so far? So model limitations and considerations. So the authors intended to make this an adversarial model. So they were trying to prove that you could learn something secret about a person or something that they might not want public based on this model. So having proven that with a reasonable amount of accuracy, you can determine where somebody went based on this insurance breaking information, they recommended countermeasures based on their findings. So they recommended first that you use a secure party, third party for evaluation. This could work, but also has similar security risks. You could avoid using brake signals for the user driving habit-based auto insurance. You can avoid using the CAN bus reader, or you could perturb the data and take it at something less than 100 hertz. And they recommended that you could add noise. But as we learned, there's drawbacks and advantages to all of these. Limitations of the model, when they encountered several consecutive road sections within 10 meters, so if there was if you're in a parking lot, for example, it was difficult for the model to distinguish what was going on. And then routes with fewer than 10 nodes, so very short paths, short trips, without a lot going on, the model struggled. And they noted that they did have a small sample size of less than 25 participants. Okay. Any questions?
Yeah, thanks. So, can any questions, anyone?
I have a question.
Yeah, go ahead.
So for their study, were all the drivers in the same region, or were they kind of spread out in different areas and situations?
So actually, they did the
They were
study
all
with,
within 450 kilometers square. So they're all in they're all in the same like Midwest region. And they all drove the same type of car.
Actually, it's kind of worse than that. So I had a chance to speak with the first author on this paper. So they actually just did it with one car. So there are also questions about whether this would generalize across cars, right? I mean, in a sense, you obviously in real life are not going to have the luxury of training a new model for each car driver pair. So there are also issues about generalizability. Another one was whether this thing will work with vehicles which have regenerative braking. So now, of course, electric vehicles have regenerative braking, but also some of the ICE cars, gas cars also have regenerative braking to some extent. Okay, so I guess the thing is you could have a slow down and take the turn and all without actually ever hitting the brake. With regenerative one. So that's another one. But so the results are based on one car. I think relatively little generalizability. But on the other hand, at an intuitive level, what their story is certainly plausible, right? I mean, we brake at intersections, and mapping information is available, and any other braking incidents are kind of confounders. One assumption that they also make is that they know the starting point, and they also rely on information about the current traffic average traffic speed on that road segment. So they kind of make use of those things also. So I guess therefore you kind of pointed out that a particular driver may be quite off from that current average speed. So that is a confounder. So there are issues, but I think I can imagine that given a long enough trace and given that braking and intersections do seem to have some correspondence, it's a plausible thing. Any other questions or comments? Okay, I guess we move on to the last talk.
Hi, can you see my screen?
Yes, we can. Please go ahead.
Great. Here I'm presenting the paper charting the attack surface of trigger action IoT platforms. So this paper gives a high overview. It's mainly exploring how can the attacker using trigger actions to do some malicious act without installing additional things. So in this presentation, I will be discussing the backgrounds and show the threat model. Then following the paper, we're going to see some vulnerabilities they generalized, and the iRuler is a tool they use, they built in this paper, and showing, and also their NLP model used to infer some inter-rule information, and the experiments they did, and finally a conclusion. So some background information. First of all, what is trigger action program? Trigger action program is actually specifies that a certain trigger events occurs, and that leads to one or more actions will be executed later. If you have ever used this FFT or on your iPhone, it will be the shortcut program, I believe. Then you may have some experience with that. For example, you can set the shortcut is if temperature exceeds 30 degrees, then open my window, provided you have all those IoT devices installed in your home. And with that user set rule, an attacker may say that may trigger your Alexa, your home device, to say trigger heater, so that your temperature will go over 30 degrees and your window will be open, which means the attacker can get a means to access your home. And the reason, the motivation behind this paper is there are studies showing that about 80% of automation requires typical users to represent their program by a trigger action program, because it is easier to do than traditional programming and gives user a lot of flexibility to do whatever they want to set as. And here, there are some platforms showed by the paper. And in this paper, it's mainly using the datasets of IFTTT from other datasets like Microsoft Flow, Zapier. They don't have an open access data set, so they cannot, for those platforms, they cannot present their modeling on those. And before, on the previous page, we showed a simple trigger action. When the temperature is rising above 30 degrees, then an event will happen. Turn on the window. The simple event is not that dangerous suspect to attackers attack, but there are some other chained rules that is more dangerous, and because there are explicitly chained and implicitly chained, as shown in these pictures, the attacker can exploit more in, and this is the main focus of this paper, to use some solver to figure out what are the rules going to lead to some vulnerabilities. And here, for the explicit chain, well, a simple example is A's action. Well, for explicit one, A's and B's trigger will belong to the same service. So, even simpler one is executing A's action will satisfy B's trigger event. And for the implicit ones is what we described, an environment change that user may not be aware of. And other than this trigger acting, there are two concepts to be clarified. One is model checking, that is to check if a system meets a specific specification by systematically exploring the system states. In this paper, it utilized SMT, that is stands for satisfiability module theorem solving, to traverse their graph to see whether it will land to some vulnerable states. But this paper did not actually go in to discuss what is SMT techniques, because it's a whole other thing. And the other idea to clear is the rewriting logic. Rewriting logic is actually a simple thing, that is just to map your system states from a literal view to a mathematical view, giving you a highly mathematical expression. For L to R, it means that there are some states satisfying L pattern will be transited to a system state satisfying the R pattern, a simple state transition. And in the threat model, this is targeting as the raw level attacks, which means the attacker are trying to subvert the intent of the end user by exploiting some interaction of those trigger action programming, those rules preset by the users. And the rules itself is actually legitimately installed by the users. There are other studies exploring the communication protocols, some bug inside the application operating system itself. But this paper, it is actually using the rules that is already installed, legitimately installed by the users. It can be explored in three ways. First one is just through direct exploration. the attacker may discover some vulnerability interaction between two actually good apps that is not mean to harm the users, or invoke the trigger events through some third-party service. The second one is using targeted rules. So it is essentially just to trick users into install some rules that enable attack. For example, just using some phishing or some social engineering. The last one is malicious apps. So attacker will actually distribute the app that is malicious and contains some hidden functionality users don't know about to install and invoke those rules. In the highlight overview, we'll say that in this paper, the tool actually built a state graph to traverse to see whether each path will actually end up in one of the vulnerabilities. So at the beginning of this paper, the author actually generalized all the vulnerability states into 6 general cases. Those are the 6 states that can be explored by the attacker to cause some unwanted behavior. The first one is conditional bypass. In this case, as illustrated by this graph here, it is that a condition may be bypassed because there are multiple rules that is all going to this end result. For example, if you set 2 rules, the first one is temperature higher than 30 degrees. When I am at home and the time is between 8 and 6, then open the window. And there are also a second rule that says that if temperature is higher than 30 degrees, then open the window. Obviously, the first rule will be ignored because there's a redundancy there. The second one is the condition block. So it means that a given condition is simply unsatisfiable, like the previous one. For example, if the user set a rule, if the motion is detected at the door when the home is in the armed state, then send the user a notification. But if the user don't have a rule to set the home in the armed state, that means this condition can never be achieved. And the other one is there's a conflicting in the block. For example, if the motion detects the door triggered, but then send a notification. But if there's another rule that says that if the motion is detected at the door, then disarm the home, then those are actually conflicting, causing one of the rules to be unapplicable. The third one is action reverting. It is pretty obvious that it's essentially toggling the state. The state change causes some extra behaviors that eventually will toggle the state back. The last one is action conflicting. The fourth one, actually, there are 2 more. So this one is actual action conflicting. So when a motion is detected, for example, when a motion is detected, then unlock the door. And there's another rule that says every day at 11 o'clock, lock the door. Then for those 2 sets of the rule, when it's at 11 p.m., it is conflict because if a motion is detected, then the door don't know whether it's locked or unlocked. The last 2 is action looping is the action that this 2 is on activation. For example, if you say you want to turn off the living room's light when the home state is away, and then there's another rule that says turn on the bedroom light when the living room light is on, then it will be causing the whole state into a looping. The last one is action duplicate. Actually, here the example we gave, the definition for action looping is a specific case for action duplicate. So basically, action duplicate is action being invoked by the same of different triggers again and again. So after generalize those vulnerabilities, the author developed a tool called iRuler to parse and for user to understand whether there's a vulnerability in their current setting. Then we're going to discuss each module. For in this graph, the yellow ones are the user's input, and the green ones are swappable things. So the raw parser can be swapped when you are using different apps, and the device and service metadata is related to a device, and the model builder and the tracking engine is what stays there to analyze the graph. So first one, we're going to discuss the raw parser. Raw parser is to extract all the raws in the apps and transforms the raw into uniform raw representation. And after that, the raw representation will be fitted into the model builder here, and the model builder will transform into an interrepresentation to give it to a track engine. Here's the example format of how the what is the raw representation looks like. It is represented here in a regular expression, so it's one more action here. So it's some details that we're not going into right now. And after the raw parser passes the raw into the representation, then the model builder will generate the intermediate representation from those raw representation. Those intermediate representation will eventually be fitted into the check engine to give users results. And the model builder, in addition to the raw representation generated by the raw parser here, it will also take in the deployment configuration and the device service metadata in to generate that interrepresentation, because interrepresentation includes some more information. So we're going to see it later. So in iRuler, the model will be essentially all of them is an event-based transition system, so that each event will make the system go into a different state, and each transition is written in the rewrite logic that we explained before. There are essentially five different states of the five different aspects of the IoT device, because for IoT devices there are different aspects that you will want to model it in different ways. First is the device service model. Essentially, it's just telling you each device has a set of different attributors. So it's representing the state of the device and supported command. For example, for the device heater, it supports the command switch. Then the device state transition, it tells you the state of each device transition. For example, the switch off can be transit to a switch on. There's some other things. Environment modeling is the states associated with environment. The environment is mostly attributed to the implicit transitions. For example, your temperature. For example, your humidity. Another thing related is the time modeling. Naturally, obviously, it's related to time. And the device service metadata is your device deployment, what kind of device it is, and where it will be located, deployed by the user. The generated result is intermediate representation. As you see here, is generated. It is in a statement that is defined here in this format, and the transition is described in the rewrite logic. And for example, the first one is saying that turn on of the model situation in which temperature sensed by the sensor exceeds the set temperature, then the air condition will be turned off. That is, then the second one similarly is turn off when the temperature is reached to a certain point. Then it's the one related to time. The check engine. Before, we have already imported all the IR from the builder. Then the check engine using rewrite module SMT. That is a solver that is used to discover those inter-row vulnerabilities that is generalized by the author into 6 categories. Rewrite modular SMT is a symbolic technique combining the power of rewrite module theories, SMT solving, and model checking. So the paper didn't go into that because it's a whole big topic there. So essentially, what it does, it will be traversing all the states and tells you whether it fall into one of the vulnerabilities or not. In the iRuler, there's a search command available that to tell you whether giving your search command, it will tell you you will need to specify your starting point and some boundaries. Then it will tell you whether it falls into one of the vulnerabilities. The search command will return either a vulnerable state reached by the initial state, or there's no solution, which tells you there's no vulnerability search from that SMT solving. Those parts are the main parts of iRuler, and in this paper, they also presented the NLP-based information flow analysis. Really, the reason behind that is to make the tool actually usable, because those big platforms are actually proprietary. They are not open source, so you cannot access those applets published by the developers to do your analysis directly, which impose obstacles to actually evaluate the performance and actually for the usabilities. So what they did is using a NLP tool to actually extract all the information from IFTTT website, go through all those developed applets, to use NLP to analysis what are the input triggers, what are the events, to then perform their analysis using their whole iRuler system. And for their NLP system, the goal is to learn a function that maps the action and trigger pair from a service to a binary output, specify whether information flow exists from A to T, that is a trigger, action to trigger, to essentially, because the lazy way to do so is you can look at all the actions, all the triggers, and just to link all of them together. But you say everyone has a connection to each other, but that will be giving you a lot of results, which makes it infeasible to actually solve. For example, you are in one of the applets, you will see there's a lock action, and there's another humidity rise above trigger. Actually, the lock action will not trigger the humidity rise trigger. So they want to use the NLP tool to better limit the scope of this graph. In this NLP tool, there are two main parts. They use syntactic analyzer to get those syntactic elements, then feed into a semantic analyzer to actually get the model out and to analyze whether there's a flow or not. So for the synthetic element extraction, they are using POS, tagging, and dependency parsing using Stanford Core NLP libraries. So one thing they did specifically because of their task here, which is the action trigger platform programming. What they did is to detect and exclude named entities from each description. For example, you will see Alexa clock. you will say Alexa speaker, even though they both have the name Alexa, but the speaker and the clock is actually not related. They're just the brand name. So they identify those. They also identify and they remove those. And for the rest of it, it's just a standard Stanford core NLP library. And later on, when we see the limitations of this NLP model of this paper, they will also discuss the NLP result is not very good, which result in some false negative in the false positive in their system. So I think maybe just by using a better NLP fitted for their task, maybe to trim it more to their task, they will get better results. But anyway, the NLP is just a tool for them to overcome in that proprietary software domain. And then they will fit the result from the syntactic element into the semantic feature extraction. This is essentially use the word embedding to encode semantic relationship of those action trigger as a vector of numeric features. After that, you have the tree relationship between the action and triggers. Then it will become a classification. It's just a binary classification to see whether there's actually a link between your trigger and action. So they did a supervised binary classification learning on that. And for this, the supervised is, when you say supervised, it means it needs ground truth. And for the ground truth, actually just the first author and second author spent about 50 hours of man hour onto this and to label them manually. And for their binary classification, 1 represents existence of law, and 0 represents the exist on the contrary. So for this classification, they employed 4 models: SVM, random forest, logic representation. So one thing to be sure here is, as we here see the false negative value here, false negative actually means that they attacks the whole attack surface model is conservative, which means that false positive here is too conservative, which means when there is no link between those two actions, it actually think there is a link in between. They contributed mostly to two reasons. Most of the reason is connected to their NLP tool, how they are doing the whole post-tagging thing. And the second thing is because they are doing NLP, so their approach is largely depends on accurate text description, which may not always be true, because they just grab those texts from the website. Then after they did that, they did an evaluation. The evaluation is on a data set bought from IFTTT website. The reason they are drawing from the IFTTT data set is, first of all, it's a popular one. Secondly, from other workflow like Microsoft Flow and Zapier, they are actually closed proprietary environment platforms, so they cannot scrap data from that. So they are able to identify more than 300 applets. Each applet is actually just an automatic script, and 674 service. And here are the results from their iRuler. So random strategy is actually just picking random data, is picking random sets of rules and to analyze whether it will be resolving in one of the vulnerabilities, and it is used here as the benchmark. And the install count strategy is they are using IFFT actually publish a data set to tell you for each applet the number of installation. They just normalize those install counts for each applet to perform a weighted calculation on of the vulnerabilities, and after that they will do a random walk on the graph starting from a random point to see how much of them will be resulting in one of the vulnerabilities. And the service-based strategy is they will just select a small number of services here from 674, then randomly selecting our rules from those services. And so the idea is, because they're randomly selecting, and the strategy will reflect that what user is likely to use only for a small number of services. And those two are the author-based strategy. I cropped off the name here. The author-based strategy is essentially is based on the installation. Here it's based on the service. Here it's based on the author who are actually publishing because author do publish duplicated applets, so they are including duplication and excluding duplication to reflect their public applet data set simulation of the number of rows. From the experimental result, we classified it into 4 categories of explicit training, implicit training from actions and triggers. The way to read these tables is actually there's a total number about 200,000, that is actually 64.8 rows that are the rows that can be explicit linked to other rows, and 62,000 rows that can be explicit linked by other rows. So other rows are explicitly linked to that. And there are this 10,000, about 3.2% rows that is implicit linked to other rows. And this one is about 2% implicitly linked by other rows. And before, at the beginning, we say author generalized the attack into vulnerabilities into 6 categories, and then we were going back and actually look at those 6 categories. First, for the condition bypass and condition block, you may already say that they are disappeared. They are disappeared from the graph because they cannot analyze it due to the proprietary nature of this of the platform. So they cannot analyze the applet filters. There are applet filters built to protect those, but they cannot analyze those filters because they cannot see them. And the second one is action looping. You will see there's a larger number of action looping because it is normal for that to use it to happen, because there are small like, for example, there's a good example that they observe. So there's a user set there whenever their calendar receive appointment, and that is, then it will receive a call. And the second rule is that IFFT will make an appointment whenever users miss a call. That means if users send IFFT's call into the voicemail, then IFFT will repeatedly call them. That is one of the looping actions. And the second one is conflicting. And actual rule they observe this: they will arm the scout alarm when the user enter an area, and this second rule is turn off user's Wi-Fi when the user enters the area. But when the user's Wi-Fi is turned off, it cannot get access to the IFTTT service, which means it can no longer activate the first rule, which is armed alarm. From the observation, they also find the classic one for the action duplication.
Javed,
For action duplication is mostly because the app developer, the authors will be public the applet multiple times. So there are likely some duplication, and also there are some group duplications. For example, you can turn off all the lights in the room, and you have another one called turn off the bedroom's light. That will result in some duplications. And they think the other things, those duplications, especially those group duplications, eventually will create potentials for action duplication vulnerability in the future development of IoT deployments. And the conclusion is the motivation of this work is to help users to better diagnose the potential security. So it's just tell the user whether there's a potential flaw, vulnerability or not. It is not a platform to protect user against it. And so this work starts with generalize those inter-rule vulnerabilities. Also present a tool for those vulnerabilities to be automatically detected. Eventually, during their experiment on more than 300,000 IFTTT applets, they determined that 66% of those applets exist a potential for inter-rule vulnerabilities. And the NLP tool is here to help them to crawl the data, for them to parse the graph flow. Any questions?
Terrific, thank you. Yeah, anyone questions? I know we are quite a bit over time, but
I just have one question. One quick question.
Yeah.
So I think the code is not public, right? Which limited their analysis of vulnerability. So what are some of the vulnerabilities that they were not able to analyze because of this code?
So first of all, because the code is not public, so they have to use NLP to actually to detect those flow. So any errors in the detection will affect all those detection, because if you cannot find that flow, or if you find a false flow, that will cause some workflow to fall in one of those. And the other one is because in the platform there will be some filters that filters out those condition bypass or condition blocks that prevent it actually being deployed, but because it is closed, so it cannot detect those. It does not know whether the filter will help the user to bypass to block that, so it cannot analyze those two kind of vulnerabilities.
Right. Thank you.
thanks. Anyone else with questions? Great. Thank you, Javed. Yeah.
Thank you.
Okay, well, thanks everyone. I know this is not how we were expecting the last lecture to be, but I think it's going to be our life for rest of the academic year, I assume, pretty much. So next week, I think all of you have signed up, so I will send you out, I guess I'll make Google Calendar entries and send out invites so that you know what your slot is, but it's basically whatever you signed up for. And I sent, I guess, some other emails about like returning the equipment and all. And insofar as your report is concerned, so basically it's going to be your GitHub repo, which is where kind of the web page component should be basically your report, and all your code and all should be there. So I will send some instructions for that as well, but basically a Piazza mail saying this is my URL would suffice. And I guess from my side, officially the drop dead date for the grades is March 30. I need a few days to do the grading, so I would like to receive your material ideally by end of next week, around the time when you are doing the presentation, but certainly early the week after. So that's any questions, anyone on the logistics side? Great. Well, thank you everyone. See you next week.